Hello, and a very warm, soft welcome back to our quiet corner of the universe. Or perhaps, if this is your first visit, a gentle welcome. As you settle into your space, allow your shoulders to slowly drop, release any tension, and feel your breath begin to deepen, soft and steady. Tonight, as the stars begin their silent dance above and the world outside softens its edges, we embark upon a whispered journey into one of the cosmos's most profound and enigmatic secrets. We ponder a question that seems, at first glance, wonderfully simple, yet stretches into the very fabric of reality itself. Why, dear friend, is it utterly, completely impossible to ever capture the elusive essence of dark matter within something as earthly and tangible as a humble jar? It's a riddle whispered by the ancient void, a paradox of presence and absence, and together we shall explore its gentle mysteries, allowing our minds to drift into a landscape of quiet wonder. And should these soft ponderings bring a touch of peace to your evening, perhaps a gentle tap of the like button or a quiet subscription might help others discover our restful discussions. But for now, let's simply allow our thoughts to unfurl as we gently begin to understand this cosmic whisper. Why is it impossible to capture dark matter in a jar? A lovely question, one that brings us to the very heart of this cosmic mystery. Imagine, if you will, holding a simple glass jar in your hand. Perhaps it's an old jam jar or a beautiful clear specimen jar you might see in a museum. Now, imagine trying to catch something in it. A butterfly, a firefly, even a wisp of smoke. You can usually manage, can't you? The butterfly flutters against the glass, the firefly glows within, the smoke curls and settles. But dark matter, oh, dark matter is different. Trying to capture dark matter in a jar is like trying to catch a whisper in a fishing net, or trying to hold a dream in your cupped hands. It simply doesn't interact with the world in the way we've come to expect, not in any tangible, familiar sense. This profound elusiveness stems from its very nature, a nature so alien to our everyday experience that it redefines our understanding of what matter can truly be. Think about everything you see around you right now. The soft glow of a lamp, the patterns on your blanket, the outlines of your room fading into shadow. All of this, every bit of color and light and form, is made possible by a fundamental force called the electromagnetic force. This force is what allows light to bounce off objects and enter your eyes. It's what holds electrons to atomic nuclei, forming all the solid, liquid, and gaseous things we know. It's why you can feel the warmth of a hug or the cool smoothness of a stone. Photons, the tiny packets of light, are the messengers of this force, constantly interacting with the electrons in atoms, giving rise to all the dazzling complexity of the visible world. But dark matter? It's utterly indifferent to light. Imagine a whisper-thin veil so fine that light passes straight through it without even a shimmer. Dark matter doesn't absorb photons, it doesn't emit them, it doesn't reflect them, it doesn't scatter them, it simply ignores them. It's like a ghost moving through a sunlit room, casting no shadow, absorbing no warmth, reflecting no gleam. If a stream of dark matter particles were to flow through the filament of a light bulb, the bulb would not flicker. nor would the particles themselves glow even faintly. They wouldn't interact with the electrons in the filament, nor would they bump into the atoms of the glass. This complete lack of electromagnetic interaction means that no matter how sophisticated our cameras, no matter how powerful our telescopes, we will never see dark matter in the traditional sense. It's profoundly invisible, not just because it's far away or too dim, but because it is fundamentally incapable of showing itself through light. So our jar, made of glass that interacts beautifully with light, would be utterly useless in containing something that doesn't care about light at all. Now, let's think about touch, about solidity. What makes a rock hard, or a table sturdy? Deep within every atom, powerful forces are at play. The strong nuclear force, for instance, is the mighty glue that binds protons and neutrons together in the heart of an atom, overcoming the electrical repulsion between positively charged protons. It's astonishingly powerful, but its reach is incredibly short, like a tiny, fierce embrace. And then there's the weak nuclear force, which plays a role in certain types of radioactive decay, allowing particles to transform. These forces are essential for building the stable atoms that make up our bodies, our planet, and indeed, all the visible stars. But dark matter, it seems, is an outsider to these interactions too. It doesn't participate in the strong nuclear force. It doesn't stick to protons or neutrons in the conventional way. It's not made of the same kind of particles, quarks and leptons, that form our familiar atoms. This means you can't build a wall of strong nuclear force to contain it, because dark matter simply won't acknowledge that wall. It would be like trying to build a brick house to block the wind. The wind, though it might jostle the house, is not made of bricks and passes around or through. Dark matter, in its profound otherness, simply doesn't engage with the subatomic dance of these powerful forces. It's as if it belongs to an entirely different set of rules, a different cosmic game where our strong and weak forces are simply not invited to play. So, if dark matter doesn't interact with light, and it doesn't interact through the strong nuclear force, and only very, very rarely through the weak nuclear force, what does it do? This is where gravity comes in, our oldest and most universal cosmic force. Dark matter interacts primarily, almost exclusively, through gravity. It has mass, and because it has mass, it pulls on other things that have mass, including visible matter and other dark matter particles. This gravitational pull is precisely how we know it exists at all. It's the invisible hand guiding the rotation of galaxies, bending the paths of light from distant stars, and shaping the large-scale structure of the entire universe. But here's the crucial point for our jar. Gravity is an incredibly weak force on a local particle-to-particle scale. Think of a tiny magnet holding a paperclip against the Earth's enormous gravitational pull. That's the difference in strength we're talking about, amplified many, many times over. For dark matter particles, their individual gravitational pull is infinitesimally small. They would pass through the glass atoms of your jar, through the air particles inside, and indeed straight through your very hand without a single bump or nudge attributable to any force other than the most subtle, imperceptible whisper of gravity. Imagine our entire solar system, with its colossal sun, its majestic planets, its countless asteroids and comets, all spinning within a vast diffuse cloud or halo of dark matter. This halo is like an enormous, invisible ocean in which our galaxy swims. And within this ocean, individual dark matter particles are streaming past us constantly, billions of them every second, passing through every atom of your body, through the floorboards, through the planet itself. They flow like an unseen wind, a silent, pervasive presence. But because their interactions are so fleeting, so minuscule, so utterly dominated by the vast open spaces between atoms, they simply continue on their way, unimpeded. They don't collide with the atoms of your jar in any meaningful way. There's no splash, no ripple, no resistance. It's like trying to catch a spirit with a net woven from moonlight. The spirit, if it were there, would simply drift through the spaces, acknowledging nothing. It's truly mind-boggling, isn't it? This substance makes up about 85% of all the matter in our universe. 85%. For every kilogram of matter we can see and touch and measure, every star, every planet, every gas cloud, every cup of tea, there are nearly 6 kilograms of dark matter utterly hidden from our direct perception. It's everywhere, permeating galaxies, forming the gravitational scaffolding that holds cosmic structures together. Yet, despite its overwhelming abundance, it remains an elusive phantom at a personal scale. So, if you could somehow seal off a section of space with your jar, intending to capture a sample of this omnipresent dark matter, what would you find? Nothing, seemingly. The jar would feel empty, weigh exactly the same, and look completely transparent. The dark matter particles inside, or rather, those that happen to be passing through, the volume enclosed by your jar at that precise moment, would continue their cosmic journey, utterly indifferent to their momentary confinement. They would stream through the atoms of the glass, traverse the empty space inside, and flow out the other side as if the jar had never been there at all. They wouldn't bounce off the glass walls, wouldn't build up pressure, wouldn't form a detectable substance. The very concept of capturing implies interaction, containment, a boundary that dark matter simply glides past. It's a profound testament to its non-interacting nature. Plun. This astonishing elusiveness, this cosmic shyness, is precisely why dark matter presents such a profound challenge to scientists. We know it's there, shaping the universe with its invisible gravitational hand. But how do we ever hope to prove its existence directly if we can't capture it, can't see it, can't touch it? It leads us to ponder the very limits of our understanding, inviting us to invent new ways of sensing the universe, new instruments and new concepts to peek behind this cosmic curtain. And so, as the night deepens, we are left not with an empty jar, but with a universe brimming with unseen wonder, prompting us to ask, if we cannot capture it, how then do we hope to finally detect its silent passage? Now you might wonder, if dark matter is so abundant, if it's all around us, why can't we simply reach out and touch it? But here's a curious thought that might drift into your mind as you settle down, like a gentle wisp of fog. If it's so abundant, if it's all around us, permeating everything, why can't we simply catch it? Why is it truly impossible to capture dark matter in a jar? You might picture a glass jar, perhaps one you use for fireflies on a warm summer evening, hoping to hold a piece of the cosmos's deepest secret. But alas, such a simple act, so easy with ordinary things, becomes an impossible dream with dark matter. To understand why, we must first think about what it truly means to capture something. When you put a firefly in a jar, the glass walls act as a barrier. The atoms in the glass repel the atoms of the firefly, and the light the firefly emits bounces off the glass, making it visible inside. This familiar interaction, this push and pull, this reflection of light, is all thanks to a fundamental force of nature called the electromagnetic force. It's the very glue that holds atoms together, allows chemicals to react, gives objects their solidity, and carries all light and radio waves. It's why you can feel the chair you're sitting on, why your eyes can see these words, and why a jar can hold anything at all. But dark matter, as its name profoundly suggests, doesn't interact with light. It doesn't feel the electromagnetic force in any significant way. Imagine a ghost, a whisper in the wind that passes through walls and people alike, leaving no trace, no shadow. That's dark matter, in essence. It doesn't absorb light. It doesn't reflect light. And crucially, it doesn't even emit light. It is truly, wonderfully, and utterly dark. This means that a jar, no matter how perfectly sealed, no matter how thick its walls, is utterly meaningless to dark matter. Its particles would simply drift through the glass atoms, through the air molecules, through anything you put inside, as if they weren't there at all. Think of it like trying to catch a whisper in a butterfly net. The net, designed to interact with physical wings, has no effect on the sound waves of a whisper. Or perhaps, imagine trying to hold a gust of wind in your hands. The wind passes through your fingers, unseen, unfelt, unless it carries dust or bends a tree. Dark matter is like that pure, invisible wind, but one that passes through everything, including you, without a single whisper of a touch. Its elusiveness goes even deeper. Not only does it ignore the electromagnetic force, but it also largely ignores the strong nuclear force, the mighty power that binds atomic nuclei together. This means it doesn't participate in the incredibly energetic reactions that create stars or fuel supernova explosions. It is, to our familiar universe, largely an indifferent spectator, passing through the cosmic drama without taking part in the visible show. So what does dark matter interact with? Primarily, it feels the gentle universal tug of gravity. This is how we know it's there at all. We see its gravitational embrace on galaxies, making them spin faster than they should, like an invisible hand keeping the stars from flying off into space. We observe its gravitational lensing, bending the light from distant galaxies, revealing its hidden mass. But gravity, while powerful on cosmic scales, is incredibly weak at the particle level. It's the weakest of all the fundamental forces, and it operates over vast distances, not in the intimate push and pull needed to contain something in a jar. And then there's the weak nuclear force, the force responsible for certain types of radioactive decay. While theoretically, some forms of dark matter, often called weakly interacting massive particles, or WIMPs, might feel the weak force, the interaction is incredibly rare, a cosmic whisper indeed almost imperceptible. Imagine a vast ocean filled with countless tiny, silent fish. We, ordinary matter, are like scattered coral reefs, These dark matter fish swim through the entire ocean, passing through the coral, never touching, never feeling the currents created by the reefs, rarely ever brushing against another. The chance of one of these WIMPs, these elusive dark matter particles, actually colliding with an atom in your jar or in your hand, or even in a sophisticated detector, is astronomically small. It's like hoping two specific grains of sand, chosen randomly from all the beaches in the world, would precisely collide at a particular moment in time. Other candidates for dark matter, such as theoretical particles called actions, would interact even less, if at all, through the weak force, making them even more ghostly. The sheer cross-section, which is a measure of how likely two particles are to interact, is so vanishingly small for dark matter and ordinary matter that for all practical purposes they simply ghost through each other. So, when we picture capturing dark matter in a jar, we're asking it to do something fundamentally against its nature. We're asking it to stop ignoring the electromagnetic force, to suddenly become solid, to reflect light, to feel the push of glass. But dark matter simply doesn't play by those rules. It's not that we haven't found the right jar, it's that the concept of a jar, a physical container designed to hold electromagnetically interacting matter, is utterly meaningless to something that exists in a different realm of fundamental interaction. It flows through our world, a silent, invisible tide, its presence only revealed by its profound gravitational influence on the grandest scales. It's there, but not in a way that our everyday senses or simple containers can ever truly grasp. And so, while a jar is useless, the quest to understand dark matter continues in much more intricate ways. We can't put it in a bottle. But perhaps, if we listen closely enough, if we build instruments sensitive enough to detect even the faintest of its whispers, we might just catch a fleeting glimpse of its elusive nature, not by capturing it, but by observing the tiny, rare disturbances it creates. Having explored why dark matter ignores electromagnetic forces, let's consider what dark matter might actually be. Imagine, if you will, the most elusive whisper, the softest shadow, a ghost that drifts through walls without so much as disturbing a dust motes. That, my dear listener, is a little like trying to grasp dark matter. The simple answer to why we cannot capture it in a jar is deeply woven into its very nature. Dark matter, by its very definition, barely interacts with anything we know and understand. It doesn't reflect light, so we can't see it. It doesn't feel the strong nuclear force, so it won't stick to atoms. It doesn't carry an electric charge, so it won't be attracted or repelled by magnets, nor will it interact with the electrons and protons that make up the solid structure of our jar, or the air inside it, or even the very atoms of your hand. Think of it as an ethereal current, flowing through everything, everywhere, all the time. Billions upon billions of these mysterious particles are passing through your body right now, through the earth, through the very bed you're resting in, entirely unnoticed. They are like guests at an unimaginably crowded party, yet they move through the throngs as if everyone else is transparent. Our jar, no matter how sturdy or how perfectly sealed, is simply a collection of ordinary matter full of empty space at the atomic level, and even more empty space between atoms. For dark matter, our jar is not a barrier, but an invitation to pass right through, as if it were not there at all. This profound elusiveness is why scientists have created a veritable theoretical zoo of candidates, each a brilliant hypothesis attempting to explain what this invisible presence might be. Each candidate offers a slightly different reason for its shyness, its reluctance to be caught, and its preferred way of gliding past our everyday reality. It's like trying to describe a dream to someone who has never slept. We use the language we have, but the true experience remains just beyond our grasp. One of the most popular residents in this theoretical zoo, and perhaps the star attraction, is the WIMP, which stands for a weakly interacting massive particle. Imagine a tiny, extraordinarily heavy pebble, far, far smaller than an atom, yet possessing significant mass, perhaps hundreds or even thousands of times the mass of a proton. Now imagine this pebble is only interested in playing a game of cosmic tag under the most exceptional circumstances. The weakly interacting part of its name refers to the weak nuclear force, one of the four fundamental forces of nature responsible for things like radioactive decay. Unlike electromagnetism or the strong force, the weak force is incredibly short-ranged and, well, weak. So, while a WIMP could theoretically bump into an ordinary atom, the chances are astronomically small, like 2 single grains of sand colliding in a desert the size of our solar system. For these particles, a jar is less a container and more a loose arrangement of widely spaced atoms through which they simply breeze. They are not captured because they have almost no desire to stop or interact with the atoms that make up the jar's walls. They don't see the jar in the way light or everyday particles would. Then we have the pondering, a candidate that occupies a very different corner of our theoretical zoo. If WIMPs are the heavy, shy boulders, actions are the ethereal, fleeting wisps, incredibly light, perhaps a billionth or even a trillionth of the mass of an electron. They were originally proposed not to explain dark matter directly, but to solve a puzzling problem in quantum chromodynamics, the theory of the strong nuclear force. Their interaction with ordinary matter is even more minuscule than that of a WIMP. Picture the faint echo of a whisper in an infinite canyon. That's how subtle an axion's touch might be. They are so indifferent to our world that trying to catch one in a jar would be akin to trying to scoop up the silence between 2 heartbeats. However, axions have a fascinating quirk. In the presence of extremely strong magnetic fields, they might, just might, fleetingly convert into a tiny flicker of light, a photon. This potential interaction is the basis for some of the most ingenious experiments seeking them out, like a fisherman using the subtlest of baits to catch the most invisible of fish, rather than trying to net the entire ocean. The zoo also once housed a collection of much larger, more conventional dark objects dubbed MACOs, or massive astrophysical compact halo objects. These were not new exotic particles at all, but rather familiar cosmic objects that simply don't emit much light. Things like brown dwarfs, failed stars, white dwarfs, or even primordial black holes formed in the very early universe. For a while, scientists considered whether the gravitational pull of dark matter might simply be due to a vast number of these dimmer cosmic residents. However, extensive surveys, peering across the galaxy for instances where these MACOs might gravitationally lens the light of background stars, have largely ruled them out as the dominant component of dark matter. While they exist, they simply aren't numerous enough to account for the immense gravitational influence attributed to dark matter. This meant our search had to turn back to the truly exotic, the truly unseen, beyond just dark versions of things we already knew. Beyond WIMPs and actions, the theoretical zoo expands further, showcasing the boundless creativity of physics. We have sterile neutrinos, which would be heavier versions of the neutrinos we already know, but with an even greater reluctance to interact. Our regular neutrinos interact via the weak force, but sterile neutrinos would be even more standoffish, perhaps only engaging through gravity, making them incredibly difficult to distinguish from the background noise of the cosmos. Then there are ideas of entire hidden sectors, or dark sectors, realms of particles that interact among themselves through their own dark forces, and only very rarely, very feebly, exchange a subtle hello with our ordinary matter through a dark photon or a similar intermediary. And for those who dream of a more symmetrical universe, supersymmetry, SUSY, offers candidates like the neutralino, which are often specific types of WIMPs, representing the lightest, stable, supersymmetric partner of particles we already know, completing a grand cosmic mirror image. All these different denizens of the theoretical zoo, from the heavy WIMP to the whisper-like axion, share one defining characteristic that makes them impossible to capture in a jar: their almost utter indifference to the electromagnetic and strong nuclear forces that bind our everyday world together. They simply do not feel the presence of the jar's atoms. They do not collide in a way that would cause them to lose energy and settle inside. Even if a single dark matter particle did interact with an atom in your jar, the chances are it would be a fleeting, glancing blow, sending the dark matter particle on its way without leaving a trace that could be observed by the unaided eye or held by material bonds. So, while the dream of a jar filled with the invisible, tantalizing substance of dark matter remains just that, a dream, the tireless work of scientists continues. They are not trying to catch dark matter in a jar, but rather to devise ingenious ways to coax out its incredibly rare whispers, to catch the faintest ripple of its passage. They are building detectors like vast, sensitive ears, listening for a sound that might only be heard once in a million years, or eyes that can perceive a shimmer where there should be only darkness. And it is to these incredible efforts, these laboratories deep underground and sensors far in space, that we turn next in our journey through the mysteries of the cosmos. We've explored the theoretical candidates for dark matter, but there's another crucial reason why a simple jar could never hold these particles. Picture this: a gleaming glass jar, perhaps one you use for fireflies on a warm summer night, or to store your grandmother's favorite cookies. Now, imagine trying to scoop up a piece of the universe's greatest mystery, dark matter, and contain it within that jar just for a moment to study it. The idea is so tantalizing, so human in its desire to hold and understand, yet, as we whisper into the quiet vastness of space, it remains profoundly impossible. But to understand why, we must first gently reacquaint ourselves with dark matter itself. It's not just a fancy name, it's an invisible architect shaping the cosmos. Roughly 27% of our universe's total mass and energy content is thought to be this enigmatic substance. We know it's there not because we've ever seen it or felt it or even directly touched it. We know it's there because we observe its gravitational fingerprints across the universe. Galaxies spin faster than they should, vast cosmic webs are held together, and light from distant stars bends in ways that only massive, unseen structures could explain. These are the whispers of dark matter, pulling on the visible universe with its silent, unseen hand. What makes any container capable of holding something? It all comes down to the fundamental forces of nature. When you put a cookie in a jar, the electromagnetic force is at play. The electrons in the atoms of the cookie repel the electrons in the atoms of the glass, creating a barrier. The jar's walls are solid because the electromagnetic forces between its atoms are incredibly strong, binding them together. Light, too, interacts with this force. It bounces off the glass, allowing us to see the jar and its contents. Every solid object, every liquid, every gas we interact with in our daily lives is primarily held together and contained by the electromagnetic force. But here's the crucial, quiet truth about dark matter. It doesn't play by those rules. Dark matter, by its very definition, does not interact with the electromagnetic force. It has no electric charge, it doesn't absorb or emit light, and it doesn't reflect light. Imagine trying to catch a whisper in a net, or trying to bottle a ghost. It would simply pass right through the mesh or right through the glass, as if they weren't even there. The particles of dark matter, often hypothesized as weakly interacting massive particles, or WIMPs, are so weakly interacting that they essentially ghost through ordinary matter. They sail through your jar, through your hand, through the earth itself, without a whisper of interaction. So, if not the electromagnetic force, what about gravity? After all, we just said dark matter interacts gravitationally. And gravity is what holds us to the Earth, what keeps planets in orbit, and what pulls galaxies together. Surely the gravitational pull of your jar could contain dark matter? This is where we encounter the profound weakness of gravity, especially on a human scale. It might sound strange to call gravity weak, given its cosmic power, but compared to the other fundamental forces, it is astonishingly feeble. Think for a moment about a small refrigerator magnet. That tiny magnet, holding a paper clip to your fridge, is generating an electromagnetic force strong enough to overcome the gravitational pull of the entire Earth on that paper clip. The Earth, a colossal sphere of rock and iron, exerts a gravitational force that is utterly dwarfed by the minuscule electromagnetic force of a few atoms in a small magnet. This startling comparison highlights just how weak gravity truly is at small scales. On the vast stage of the cosmos, where masses are astronomical, planets, stars, galaxies, gravity reigns supreme because its influence extends infinitely and adds up over immense distances and colossal amounts of matter. But in the tiny realm of a glass jar, filled with only a few hundred grams of glass and air, its gravitational pull is utterly negligible. The gravitational attraction between a hypothetical dark matter particle and the atoms of your jar would be so incredibly small, so fleeting, that it would have no chance whatsoever of holding the dark matter particle inside. A single breath could exert more force than the combined gravitational pull of your entire house on a dark matter particle. Furthermore, dark matter particles are not static. We believe they are constantly streaming through space, moving at incredible velocities, hundreds of kilometers per second, as part of the vast dark matter halos that envelop galaxies like our own Milky Way. Even if a stray dark matter particle happened to drift into your jar, its momentum, combined with the almost non-existent interaction with the jar's walls, electromagnetically, and its negligible gravitational attraction to the jar, would mean it would simply continue its journey, passing straight out the other side as effortlessly as it entered. It wouldn't slow down, wouldn't bounce, wouldn't stick. It would be like trying to catch a swift, invisible current in a sieve made of starlight and wishes. Dark matter is also incredibly diffuse in our local neighborhood. While it forms massive halos around galaxies, the density of dark matter particles in any given cubic meter of space around Earth is estimated to be very low. Even if you could somehow overcome the interaction problem, you'd likely capture almost nothing. It's like trying to fill your jar with fog from a vast, silent, invisible ocean. So, the jar remains empty, a testament not to our failure, but to the peculiar nature of the universe's invisible scaffolding. Dark matter cannot be captured in a jar because it ignores the forces that make jars solid, and the one force it does acknowledge, gravity, is far too weak on our human scale to ever pin it down. It is the very definition of the unconfinable, a ghostly presence that passes through us and everything we know, a silent river flowing through the cosmos, forever beyond our grasp. It's a humbling thought, a reminder of the subtle, powerful forces that shape our reality in ways we can only infer. But if we cannot capture it, how do we begin to truly sense its presence, to tease out its secrets from the vastness? Perhaps we must look not for a jar, but for something far more intricate, far more sensitive, listening for those faintest of whispers in the dark. Now, having understood gravity's weakness, let's consider where dark matter actually is. Imagine, if you will, a vast invisible ocean that permeates everything. It flows not just around the stars and planets, but through them, through you, through every atom and every empty space in between. This is the essence of dark matter's cosmic distribution, a silent, pervasive presence that moves unhindered through the very fabric of our universe. It is not merely somewhere out there in the void between galaxies. It is here, right now, a whisper passing through your sleeping form, a gentle current through the very bed you rest upon. This boundless freedom, this ability to pass through everything, stems from a profound lack of engagement with the everyday world we know. Our universe, with its vibrant tapestry of light and color, solid objects and flowing liquids, is largely orchestrated by four fundamental forces. You are familiar with gravity, which pulls us gently to the earth and holds the stars in their dance. Then there are the strong and weak nuclear forces, microscopic architects that bind the very heart of atoms and orchestrate certain radioactive decays. And finally, the electromagnetic force, the dazzling maestro that gives us light, chemistry, electricity, and all the tangible sensations of touch and sight. This force is what allows atoms to hold together, to form molecules, to reflect light, to feel solid against your hand, and ultimately, to make up the glass of a jar. But dark matter, in its enigmatic dance, largely ignores three of these four fundamental forces. It's a ghost to the strong nuclear force, the powerful glue that holds atomic nuclei together. Where protons and neutrons huddle closely, bound by an almost unimaginable strength, dark matter particles feel no such tug or embrace. They simply drift through the very core of atoms, unconcerned by the ferocious energy that would rip apart any ordinary matter trying to penetrate. Imagine trying to hold a wisp of smoke, not with your hands, but with the molecular bonds of a solid wall. The smoke, unimpeded, would merely swirl on through, utterly indifferent to the wall's existence as a barrier. And even more significantly for our everyday experience, dark matter is oblivious to the electromagnetic force. This is the grand conductor of light and all its manifestations. It's why you can see the stars, why your eyes detect the warm glow of a lamp, why colors exist, and why a solid object can stop another. When light strikes an object, it's the electromagnetic force at play, with electrons in the object absorbing and re-emitting photons, or reflecting them, or simply blocking their path. But dark matter particles carry no electric charge. They do not interact with photons, the tiny packets of light and electromagnetic energy. This means they cannot absorb light, cannot emit light, cannot reflect light, and cannot even cast a shadow. They are utterly invisible, truly dark, not in the sense of being black, but in the sense of having no interaction whatsoever with the light that defines our visible world. Trying to capture something that light cannot even acknowledge, that sound cannot echo from, that touch cannot register, is like trying to catch a dream in a net made of sunlight. And while there is a faint whisper of a possibility that dark matter might interact ever so subtly with the weak nuclear force, the force responsible for certain types of radioactive decay and the interactions of neutrinos, any such interaction is incredibly astronomically weak. Neutrinos themselves are already the universe's most famous escape artists, tiny particles that can pass through trillions of miles of lead without interacting with a single atom. Yet, dark matter is thought to be even more elusive, even more indifferent. For every neutrino that might occasionally bump into an atom in your body, an unthinkably vast number of dark matter particles pass through without so much as a polite acknowledgement. Think of the Earth itself, a magnificent sphere of rock and molten metal, bustling with life and vibrant energy. For ordinary matter, it's a colossal, impenetrable barrier. But for dark matter, our entire planet is like a vast, almost empty sieve, with atoms spaced so far apart on the subatomic scale that these elusive particles simply thread their way through the gaps. It's as if the Earth, the Sun, even entire galaxies are merely gossamer webs, fine and delicate, through which dark matter drifts unimpeded. You are, in this grand cosmic ballet, a collection of atoms separated by vast empty spaces, and dark matter flows through these spaces as if you weren't even there. Millions upon millions of dark matter particles are streaming through your body at this very instant, and you feel nothing. Not a tickle, not a breeze, not even the slightest hum, because they interact with virtually nothing within you. They are truly the silent, unseen passengers of the universe. This cosmic distribution, this ability to permeate everything, is precisely why dark matter is so crucial to the structure of the universe. While it ignores the strong, weak, and electromagnetic forces, it does respond to gravity. And because it's so abundant, making up about 27% of the universe's total mass energy, its collective gravitational pull is immense. It forms vast, invisible halos around galaxies, providing the gravitational scaffolding that prevents them from flying apart as they spin. It's the invisible glue that holds the largest structures of the cosmos together, shaping the cosmic web of galaxies and clusters that we observe. Without it, our universe would look very different, a much more sparsely populated and chaotic place. So, when we consider the question of capturing dark matter in a jar, the answer becomes profoundly clear. A jar, even one crafted with the densest, most impenetrable material imaginable, is utterly meaningless to a dark matter particle. Its atoms, its molecules, its solid walls, its very structure are all products of the electromagnetic force and the strong nuclear force. But dark matter particles simply do not see these forces. They glide through the electrons, slip past the nuclei, and continue on their boundless journey as if the jar were not there at all. It is like trying to catch a whisper in a tightly sealed box, or to contain a feeling with a tangible barrier. The fundamental nature of dark matter's non-interaction renders any such endeavor impossible. This profound elusiveness, however, doesn't mean we are entirely without hope in our quest to understand it. Even the faintest whisper, the most fleeting shadow, can sometimes reveal a hidden truth, and our scientists are finding ingenious ways to listen for these incredibly subtle hints, pushing the boundaries of what we thought possible to detect. And in the quiet moments of the night, we can wonder what faint echoes of its passing might one day reveal the true nature of this invisible sea. Why is it impossible to capture dark matter in a jar? Imagine for a moment that you hold a simple, clear glass jar in your hands. It's an ordinary jar, perhaps one that once held delicious jam or a cluster of fireflies on a warm summer night. Now, what if I were to ask you to use this very jar, this common everyday object, to capture something as extraordinary and elusive as dark matter? It's a natural thought, isn't it? If something exists, surely we can contain it, study it up close. But when it comes to dark matter, the answer is a resounding yet gentle no. It is, quite simply, impossible to capture dark matter in a jar, or indeed in any container we can conceive of. To understand why this is so, we need to whisper about the very nature of dark matter itself, about how it interacts, or rather, how it doesn't interact, with the world we know. Our universe, in its grand tapestry, is woven from threads of ordinary matter. The atoms that make up your bed, the air you breathe, the stars that twinkle far above. These atoms are bustling with activity, their electrons dancing around their nuclei, constantly interacting with each other through various forces. They push, they pull, they exchange tiny packets of energy, they scatter off one another, they reflect light, absorb heat. These constant interactions are what give matter its solidity, its shape, its very presence. They are why a jar can hold jam, why you can feel the warmth of a blanket, why light bounces off a mirror. But dark matter. Dark matter is a different kind of entity altogether. It is, in essence, a ghost in the cosmic machine. Its primary characteristic, the defining feature that makes it so mysterious and so challenging to detect, is its astonishingly weak interaction with ordinary matter. When we say weak, we mean almost infinitesimally so. It doesn't interact through the electromagnetic force, which is the force responsible for light, electricity, magnetism, and indeed all chemical reactions and the very structure of atoms. This means dark matter doesn't absorb light, doesn't emit light, doesn't reflect light. It is utterly invisible, passing through photons as if they weren't there. Nor does dark matter interact through the strong nuclear force, the mighty glue that binds protons and neutrons together within the hearts of atoms. This force, powerful over tiny distances, is what forms the very nuclei of all the elements. Yet, dark matter glides past these strongholds as if they were mere whispers on the wind. And while it might, hypothetically, interact through the weak nuclear force, the force responsible for certain types of radioactive decay, such interactions, if they occur at all, are predicted to be so incredibly rare, so fleeting, that they are like finding a single shy firefly in a galaxy of stars. So imagine that jar again. If you were to fill it with air, it would contain billions upon billions of oxygen and nitrogen, molecules, constantly colliding, bouncing, and interacting. But if you were to somehow open that jar to the vast cosmic currents and let the dark matter flow in, what would happen? Nothing to our senses. The dark matter particles, hypothesized to be something called WIMPs, weakly interacting massive particles, would simply stream straight through the glass walls of the jar. They would pass directly through the atoms of the air inside, never noticing them, never disturbing them. They would then pass through the floor, through the earth beneath, and out into space on the other side, utterly unimpeded. Think of it this way. Imagine standing in a vast, empty sports stadium, and once every billion years, a single, incredibly tiny, perfectly transparent billiard ball flies through the stadium. The chance of that one ball ever hitting another, or even a single atom of the stadium structure, is virtually zero. Now scale that down to the subatomic world, and you begin to grasp the challenge. The atoms in your jar, even though they seem solid and substantial to you, are mostly empty space for a particle that doesn't interact electromagnetically or strongly. The nucleus is tiny, the electrons are like distant clouds, and the rest is vacuum. For a dark matter particle, a jar is not a container. It's an impossibly vast, almost entirely empty expanse that it traverses without so much as a thought. And even the earth itself, a colossal sphere of rock and molten metal, is, to dark matter, more like a wispy fog than a solid obstacle. Billions of dark matter particles are passing through your body right now, through the chair you're sitting on, through every building and mountain on our planet, every second of every day. They leave no trace, impart no energy we can feel, because the probability of one of them ever interacting with one of your atoms is extraordinarily low. For a dark matter particle, our entire planet is merely a slightly denser region of space to pass through. Plow on. And what about gravity? We know dark matter interacts gravitationally. That's how we first inferred its existence, by observing its gravitational pull on galaxies. But gravity, while fundamental, is by far the weakest of nature's forces at the scale of particles and everyday objects. The gravitational pull of a jar, or even a planet, is utterly insufficient to capture or hold a stream of dark matter particles that are moving at incredible speeds, unaffected by any other force. It would be like trying to catch mist in a net with holes larger than the entire ocean. So, the jar remains empty, at least of dark matter. The very properties that make dark matter so crucial for the structure of the cosmos, its weak interactions, are precisely what make it impossible to simply scoop up and contain. We cannot trap it, we cannot see it directly, and we certainly cannot hold it in our hands. It slips through our grasp like a whisper through a dream. But if we cannot capture it in a jar, if it passes through everything seemingly unnoticed, then how, you might wonder, do we even begin to search for such a phantom particle? How do we hope to detect something so elusive, something that barely touches our world? Well, dear listener, that is where the true ingenuity of science comes into play. If we cannot capture it, perhaps we can, with immense patience and incredibly sensitive instruments, detect the faintest, rarest tremor of its passage. The whisper of an interaction that occurs perhaps only once in a lifetime, or even less frequently, within a vast detector. Join me next as we delve into these remarkable hunts. Our journey through the cosmos, as we gently drift through the concept of dark matter, brings us to a fascinating juncture. How do we even begin to understand something we can't see, feel, or touch? Since we can't simply scoop it into a jar, scientists must employ extraordinary methods, seeking not the dark matter itself, but the faintest whispers of its presence, or the brief, fiery moments of its creation. This brings us to two profound avenues of exploration: indirect detection and the mighty colliders. Imagine, if you will, trying to understand a secret, elusive creature that never shows itself. You might never see it directly, but you could look for its footprints, listen for the sounds it makes, or find the remnants of its meals. This is the essence of indirect detection for dark matter. It's a patient, cosmic detective story where we're not looking for dark matter itself, but for the ordinary particles it might leave behind after a significant event. Theory suggests that if two dark matter particles, perhaps drifting through the vast cosmic ocean for eons, were to cross paths and collide, they might undergo a profound transformation, an act of cosmic self-annihilation. In this moment, they would cease to be dark matter, their mysterious energy converting into something we can detect, the very particles that make up our familiar universe. These byproducts could be high-energy photons, the tiny, almost massless neutrinos, or even exotic pairs of electrons and their antimatter twins, positrons or protons and antiprotons. Think of it like this. You can't see the wind, but you can see the leaves rustling, the flags flapping, or the ripples on the water. These are the wind's annihilation products, its telltale signs. Similarly, astronomers turn their powerful telescopes and detectors towards regions of the cosmos where dark matter is thought to be most abundant, places like the very heart of our own Milky Way galaxy, the shadowy halos of dwarf spheroidal galaxies, or the colossal clusters of galaxies that dot the universe. These are our cosmic dark matter hotspots, places where the chances of two dark matter particles encountering each other are highest. Satellites, like the Fermi Gamma Ray Space Telescope, quietly orbiting above our planet, or ground-based observatories such as HESS, MAGIC, and Veritas, perched in high, clear locations, are like diligent listeners straining to catch these faint gamma-ray signals. Deep beneath the Antarctic ice, the Ice Cube Neutrino Observatory stands as a sentinel, waiting for the elusive, almost non-interacting neutrinos that might be born from dark matter annihilation. When these instruments detect a suspicious excess of high-energy particles coming from a dark matter-rich region, an excess that can't be explained by ordinary astrophysical processes, it could be a precious clue, a cosmic footprint left by dark matter's elusive dance. But herein lies the challenge, and a crucial piece of our understanding of why dark matter is impossible to capture in a jar. These signals are incredibly faint. Even in the densest regions, dark matter particles interact so rarely and so weakly that their annihilation events are few and far between. It's like trying to hear a single whisper across a vast, bustling stadium. The very act of searching for these rare, weak signals, these indirect clues, tells us just how incredibly reluctant dark matter is to interact with anything, even other dark matter particles. If its annihilation, a powerful energy conversion, is so difficult to detect, imagine trying to physically contain it with a jar made of ordinary matter. It simply slips through, unaffected. Yet our scientific curiosity doesn't stop at merely observing. Sometimes we try to create. This leads us to the second majestic approach: colliders. At facilities like the Large Hadron Collider, LHC, at CERN, deep beneath the serene Swiss and French countryside, scientists aren't just observing. They're actively trying to forge dark matter. They've built magnificent colossal machines, veritable cosmic anvils, designed to recreate the fiery conditions of the universe's earliest moments, just after the Big Bang. Here, ordinary particles, usually protons, are accelerated to nearly the speed of light, endowed with immense kinetic energy, and then smashed head-on into each other. According to Einstein's famous equation, EXmc2, this incredible energy can be briefly converted into mass, briefly creating new, heavier particles. If dark matter particles exist and are within the energy reach of these titanic collisions, then for a fleeting instant they could be born. But how do we see something that doesn't interact with our detectors? This is where the concept of missing energy becomes our beacon. Before each collision, scientists meticulously measure the total energy and momentum of the incoming particles. When the collision occurs, and if new particles are created, our detectors, which are like giant, multi-layered cameras, meticulously record the tracks and energies of every outgoing particle that does interact. If dark matter particles are produced, they would, true to their nature, pass right through these detectors without leaving a trace. They would carry away energy and momentum, effectively vanishing from our observable record. So, after the collision, when scientists add up all the energy and momentum of the detected particles, they might find that the numbers don't quite balance. There's a hole in the budget, a significant amount of energy and momentum simply gone, unaccounted for. This missing energy is the tantalizing fingerprint of something unseen, something that didn't interact with our detectors, a potential dark matter particle. It's like a magician making an object disappear. We know it was there, and now it's not. And the only explanation is that it went somewhere we can't perceive. Again, this method powerfully underscores why capturing dark matter in a jar is impossible. Even if we succeed in creating dark matter in these most extreme, high-energy environments, we don't catch it. We infer its presence only because it flies away, unseen and untouched, slipping through the very fabric of our detection equipment. The entire strategy of collider searches relies on dark matter's non-interacting nature. It's born free, and it remains free, impervious to any container we might fashion. The incredibly high energies required to even create it, combined with its immediate escape, tell us that its interaction with ordinary matter is so profoundly weak that any jar would be, to dark matter, utterly transparent and utterly porous. Both indirect detection, which seeks the faint echoes of dark matter's decay or annihilation, and collider experiments, which attempt to forge it from pure energy, paint a consistent picture. They reveal a substance woven into the cosmic tapestry, omnipresent yet ethereal, interacting with our world only through the most subtle gravitational caress or the most fleeting, almost imperceptible interactions. This profound elusiveness is the core reason it cannot be contained. But what if we try a different approach? One that looks for dark matter not just indirectly or by creation, but by feeling its very touch, however gentle. The true impossible nature of capturing dark matter in a jar isn't just about its elusive nature, but also about the immense experimental hurdles we face. Imagine, if you will, the deepest quiet, the most profound stillness. And then imagine trying to find a single, tiny, almost imperceptible whisper within that quiet. This is the heart of our challenge, the twin titans of sensitivity and background. Our journey into the invisible realm of dark matter requires instruments of almost unimaginable sensitivity. If dark matter particles interact at all, their touch upon our detectors would be the faintest caress, a whisper so soft it barely registers. It's like trying to feel the impact of a single snowflake landing on a vast frozen lake from miles away, or listening for the softest sigh in a world accustomed to thunder. We are seeking an interaction so rare, so fleeting, that it might deposit just a minuscule amount of energy, perhaps just a few electrons or a tiny flash of light, or the faintest vibration in a crystal. For our detectors to even dream of registering such an event, they must be utterly pristine, utterly silent within themselves, and utterly tuned to catch the faintest ripple. Think of it as tuning a radio to pick up a secret message broadcast from a distant star, a message so weak it's almost indistinguishable from the static of the universe itself. Every single atom within our detector needs to be perfectly still, perfectly calm, so that the faintest disturbance from an interacting dark matter particle can stand out. But here's the colossal problem. Our universe is anything but silent. It's teeming with activity, a bustling cosmic metropolis of particles. This is what we call background. Every single signal, every tiny interaction, every energetic whisper that isn't dark matter. And these backgrounds are formidable, acting like an enormous roaring waterfall that drowns out the whisper we're trying to hear. Consider cosmic rays, those high-energy particles from distant supernovae and black holes constantly showering our planet. They zip through everything, including our bodies, our homes, and yes, our delicate dark matter detectors, leaving behind undeniable trails of energy. If a cosmic ray slams into our detector, it creates a much louder signal, completely overwhelming any tiny dark matter interaction. It's like trying to find a specific, almost invisible firefly in a field swarming with millions of bright, flashing regular fireflies. Then there's the natural radioactivity all around us. The very earth beneath our feet, the air we breathe, the water in our oceans, and even the materials from which our detectors are built, all contain trace amounts of radioactive isotopes. These isotopes decay, releasing particles, alpha particles, beta particles, gamma rays, that can also interact with our detectors, mimicking the very faint signals we hope to find from dark matter. Imagine trying to hear a secret whisper in a room where every surface, every object, is constantly humming with its own tiny, gentle, but ever-present song. And let's not forget neutrinos. These ghost-like particles, born in the hearts of stars like our sun, or from exploding supernovae, or even in our own atmosphere, are themselves incredibly weakly interacting. They pass through light years of matter almost unnoticed. Yet occasionally, just occasionally, one might interact with our detector. A neutrino interaction can look very similar to a potential dark matter interaction, adding another layer of complexity to our search. It's like having multiple different kinds of invisible people walking through your house, and you're trying to identify the one specific invisible guest you're actually waiting for. So, how do scientists, with their boundless ingenuity and quiet determination, attempt to overcome this immense hurdle? They don't just build a better radio. They build an entire, silent, isolated chamber, far away from all the world's noise, and then they build the most exquisite radio imaginable within it. The first, and perhaps most intuitive strategy is shielding. To escape the relentless bombardment of cosmic rays, we literally go deep underground. Imagine descending thousands of feet into the earth, into abandoned mines or custom-built laboratories carved out of solid rock. This colossal blanket of rock, sometimes over a mile thick, acts as an incredibly effective shield, absorbing most of the cosmic rays before they can ever reach our sensitive instruments. Down there, in the silent, cool embrace of the earth, the cosmic ray flux is reduced by factors of 1,000,000 or more. It's like submerging yourself in the deepest part of the ocean to escape the storms raging on the surface. A profound quiet descends. Next, scientists obsess over ultra-pure materials. Every single component of a dark matter detector is painstakingly selected and purified to an almost unimaginable degree. Researchers spend years developing new techniques to remove even the most minuscule traces of radioactive isotopes from the materials they use. The silicon crystals, the liquid xenon, the germanium, the copper wiring, even the adhesive glues. It's a quest for atomic purity, ensuring that the detector itself isn't creating its own internal background noise. Think of it as crafting a musical instrument not just from the finest wood, but from wood so pure it has no natural resonance or hum of its own, so that only the notes you intentionally play can be heard. Many detectors are also plunged into the realm of the extreme cold, operating at cryogenic temperatures, often just a fraction of a degree above absolute zero. Why? Because at these frigid temperatures, the atoms within the detector materials barely vibrate. This stillness dramatically reduces Planck's thermal noise plow, the random jiggling of atoms that can generate spurious signals. When everything is so cold and quiet, the detector becomes incredibly sensitive to even the most minuscule energy deposition, like a perfectly still pool of water that reveals the faintest ripple from a single dropped dewdrop. Furthermore, detectors employ sophisticated veto systems. Imagine a Russian doll with multiple layers. The innermost doll is the ultra-sensitive dark matter target. Surrounding it are layers of other detectors, specifically designed to catch any known background particles, before they can reach the core. If a particle is detected in an outer veto pulsars layer, the signal from the inner detector at that moment is automatically discarded, or vetoed, because we know it wasn't a dark matter interaction. It's like having a highly trained security team at the entrance of a quiet concert hall, filtering out any unwanted noise before it can disturb the delicate music within. Finally, scientists use clever methods of event discrimination. Even after all the shielding and purification, some background events will inevitably sneak through. But different types of particles leave different fingerprints when they interact with matter. A gamma ray might deposit its energy differently than a neutron, and hopefully, a dark matter particle would leave its own unique signature. By carefully analyzing the shape, timing, and location of the energy deposited, scientists can distinguish between these different kinds of interactions, patiently sifting through countless events to identify the one longed-for signature of dark matter. It's like being an expert detective, examining the subtle clues left behind at a crime scene, knowing that the smallest detail can reveal the true identity of the perpetrator. This relentless pursuit of quiet, this meticulous fight against background, and this incredible push for sensitivity are why dark matter experiments are often monumental feats of engineering and scientific dedication. They are not merely devices, they are monuments to human curiosity, built with the hope of catching the faintest whisper from the cosmos. The expected event rates are astonishingly low, perhaps just 1 or 2 potential dark matter interactions in a ton of detector material over an entire year, or even less. This means patience, precision, and profound technological mastery are not just virtues, but absolute necessities. As we drift deeper into the mysteries of the universe, our next quiet inquiry will lead us to ponder the very fabric of space-time and how the massive, unseen influence of dark matter might subtly bend and shape the cosmos, offering yet another whisper of its presence. To imagine capturing dark matter in a jar is to conjure a comforting, almost childlike image. A simple vessel, perhaps made of shimmering glass, waiting to hold a mystery. We understand jars. They hold fireflies, pebbles, the last lingering scent of summer. They are symbols of containment, of possession, of making the intangible tangible. But as we drift deeper into the nature of dark matter, we find that the very concept of a jar, with its solid walls and sealing lid, becomes not just impractical, but a profound conceptual impossibility when applied to this elusive cosmic ingredient. Let's begin by gently considering what a jar, or indeed any solid object, is fundamentally. It's an arrangement of atoms held together by powerful electromagnetic forces. The glass itself, whether silicate or plastic, derives its solidity from the precise ballet of electrons orbiting atomic nuclei. when you try to put a pebble in a jar, or when your hand rests softly against a surface. What you're experiencing is the electromagnetic interaction between the electrons of your atoms and the electrons of the object. These tiny, negatively charged particles, orbiting the nuclei of every atom, exert forces of attraction and repulsion. It's these forces that prevent your hand from passing through the table, and it's these forces that create that firm barrier, that reassuring thud of contact when one object meets another. This electromagnetic interaction is the silent architect of nearly all our everyday experiences. The feeling of touch, the warmth of a blanket, the light that guides your way, the very structure of your hand resting gently as you listen. Now, let us introduce our ghost in the cosmic machine, dark matter. This mysterious substance, thought to make up approximately 27% of the universe's mass energy content, dances to a profoundly different tune. Dark matter is, by its very nature, fundamentally indifferent to these electromagnetic forces. It doesn't reflect light, so it is invisible to our eyes, to our telescopes, to every instrument designed to detect photons. It doesn't absorb light, so it casts no shadow, leaves no telltale trace of its passage through beams of light. Crucially, it doesn't interact with the electrons that make up the solid walls of our hypothetical jar, or indeed the electrons that define the boundaries of your own body or the Earth itself. To a dark matter particle, the atoms of the jar, the atoms of your hand, the atoms of the Earth are not solid objects at all. They are like wisps of smoke, or perhaps vast and empty spaces. Imagine a vast open field, and in it a scattering of tiny, invisible dust motes spread impossibly far apart. From a great distance, the field appears empty. But zoom in, and you see these motes, each an atom, with its nucleus and electrons. Now imagine a whisper of wind, so fine, so ethereal, that it passes between these motes without ever touching a single one. That whisper of wind is a dark matter particle. The motes are our atoms. The jar, a collection of these motes, presents no barrier. This isn't to say dark matter passes through us because our atoms are mostly empty space, though that's true in its own right. The true reason it passes through is because it simply doesn't see the forces that make the empty space between atomic nuclei feel solid to ordinary matter. For us, solidity comes from the electron shells around atoms and the electromagnetic forces that make them repel each other when they get too close. A principle often reinforced by the Pauli exclusion principle, which dictates that no two identical fermions, like electrons, can occupy the same quantum state. Dark matter particles, if they are not electrons or other known charged particles, simply ignore these rules of engagement. They have no charge, no magnetic moment, and thus no electromagnetic handle for our jar to grasp. So, if not electromagnetic, how does dark matter interact? Primarily through the most ancient and universal force, gravity. Dark matter particles exert and feel gravitational pull, just like everything else with mass. This is why we know it's there. Its collective gravity shapes galaxies, bends light, and holds the cosmic web together. But gravity, while mighty on cosmic scales, is incredibly feeble on the scale of a jar. A jar simply doesn't have enough mass to exert a gravitational pull strong enough to trap even a single dark matter particle, let alone a measurable quantity. Trying to hold dark matter in a jar using gravity would be like trying to hold an ocean with a single drop of dew. The scale of the force is utterly mismatched to the task. Beyond gravity, scientists hypothesize that dark matter might interact through the weak nuclear force. But even these interactions are thought to be exceedingly rare and fleeting, perhaps a 1 in a trillion chance encounter. These are the interactions that dedicated dark matter detectors, buried deep underground, are designed to painstakingly search for, hoping for the faintest ping from a passing dark matter particle bumping into an atomic nucleus. But even if such an interaction occurred, it wouldn't trap the particle in any meaningful sense. It would be a momentary, almost imperceptible nudge, not a capture. Plun. The conceptual impossibility of the jar analogy lies in this fundamental disconnect. The very definition of a jar, a container that physically encloses something, relies on forces that dark matter completely bypasses. It's not that we haven't found the right kind of jar, it's that the concept of jarring simply doesn't apply. It's akin to trying to catch a feeling in a net or bottling a dream. The tool is designed for a completely different class of phenomena. Dark matter doesn't bounce off matter. It passes through it as if it weren't there, a phantom breeze through a forest of trees, leaving no leaf rustled, no branch swayed. These ethereal particles, in their billions, are streaming through you right now, through the earth, through the sun, utterly oblivious to the conventional barriers we perceive as solid. They are silent cosmic travelers, ever present, yet forever beyond our grasp in the way we traditionally understand holding or containing. And so, as we close our eyes tonight, let the image of that impossible jar fade, replaced perhaps by the thought of these cosmic travelers, unburdened by the familiar forces of our world. But this inability to hold dark matter doesn't mean we can't detect it. It simply means we must learn to listen for its whisper in entirely new ways, which is precisely what we will explore as we gently turn the page to our next quiet observation. As we near the end of our cosmic journey, we confront the deeper theoretical questions that remain unanswered. This impossibility of capturing dark matter, this fundamental disconnect from our everyday world, points to profound gaps in our understanding. You could fill it with air, water, starlight, or even a tiny firefly, and for a brief time, you'd have captured a piece of the visible world. But if you were to reach out and try to scoop up dark matter, your hand would pass right through it, and your jar would remain stubbornly, utterly empty. To understand why this seemingly straightforward act is utterly impossible, we must first gently grasp what dark matter is, or rather, what we believe it to be. Imagine it as a cosmic ghost, an unseen architect of the universe. We know it's there because we can observe its immense gravitational pull on galaxies, bending light from distant stars like an invisible lens, holding vast clusters of galaxies together. Without its hidden embrace, the universe as we know it would simply unravel, spinning apart like a celestial top. Yet, despite its profound influence, it refuses to interact with light or any of the forces that govern the ordinary, luminous world we inhabit. Think about the world around you, everything you see, touch, and feel. Your soft blanket, the gentle glow of a nightlight, the very air you breathe. All of these are made of ordinary matter, composed of tiny particles like protons, neutrons, and electrons. These particles interact with each other in beautiful and complex ways. Electrons, for instance, are bound to atomic nuclei by the electromagnetic force, which also allows atoms to form molecules, creating the incredible diversity of substances around us. It's the electromagnetic force that lets light reflect off your jar, making it visible. And it's this same force that gives the jar its solidity, preventing your hand from passing through it. It allows chemical reactions to occur, paints to shine, and magnets to cling. Dark matter, however, is profoundly indifferent to all of this. It utterly ignores the electromagnetic force. This means it doesn't absorb light, reflect light, or emit light. It doesn't participate in chemical reactions, nor does it stick to anything via electrical charges. So, the moment you try to put it in a jar, it simply won't interact with the atoms that make up the glass. It would be like trying to catch a whisper in a butterfly net. The net, no matter how finely woven, is simply not designed to interact with sound waves in that way. The dark matter particles would pass through the glass atoms as if they weren't there, leaving the jar's contents unchanged and its purpose unfulfilled. But it's more than just a lack of electromagnetic interaction. Dark matter also seems to largely ignore the strong nuclear force, which binds protons and neutrons together within the nucleus of an atom. And it has, at best, an incredibly weak interaction with the weak nuclear force, which governs certain types of radioactive decay. In essence, dark matter is a stranger to the fundamental forces that weave together the tapestry of our visible world. Its primary confirmed interaction, the one we rely on to know it exists, is gravity, the weakest of all the fundamental forces, yet the one that acts across the vastest cosmic distances. Imagine particles that are so aloof, so utterly detached from our reality, that they could be flowing through your very body right now, billions upon billions of them every second, and you wouldn't feel a thing. Your atoms, the very cells that make you, are mostly empty space, but even the nuclei and electrons within them present a barrier to ordinary matter. For dark matter, however, even these tiny, dense components of atoms are largely irrelevant. It simply passes through, like an unseen current through a porous sieve. It's like trying to catch mist with your hands. The particles are there, abundant, but they refuse to coalesce or be held. This fundamental difference in how dark matter interacts, or rather, doesn't interact, with other particles is why we can't collect it. A jar works because its atoms repel other atoms, forming a solid barrier. But dark matter's hypothesized particles, whether they are the elusive WIMPs, weakly interacting massive particles, or incredibly light axions, simply don't see those atomic barriers. They don't collide. They don't stick. They don't exchange energy in a way that would allow them to be contained. They are, in a very real sense, ghosts passing through ghosts. Furthermore, the very nature of dark matter prevents it from forming the kind of structures that could be captured. Ordinary matter, the stuff of stars and planets and jars, can cool down by radiating light and then collapse under gravity to form dense objects. This cooling mechanism, facilitated by electromagnetic interactions, is essential for clumping. Dark matter, lacking these interactions, cannot cool in the same way. It spreads out in vast, diffuse halos around galaxies, providing the gravitational scaffolding, but it doesn't form dense, compact objects that one could ever hope to scoop up. It's like trying to gather sunlight into a solid block. Sunlight is everywhere. It's energy, but its fundamental nature means it cannot be solidified or contained in a physical vessel. So, while we might dream of a future where we can manipulate the fabric of reality, perhaps even capture a sliver of dark matter, for now, the gentle glass jar remains utterly powerless. The impossibility isn't a failure of ingenuity, but a profound statement about the very nature of this mysterious cosmic component. It reminds us that our universe is far stranger and more diverse than what meets the eye, or what can be held in a hand. It's a challenge to our understanding, a silent invitation to delve deeper into the unseen realms. And as we consider this unseen influence, this cosmic ghost that permeates everything yet touches nothing, we naturally begin to wonder, if dark matter is so abundant yet so elusive, what else might be out there, woven into the fabric of reality, waiting to be discovered? Our journey into the theoretical frontiers of physics is filled with such questions, each one a thread leading us deeper into the unknown, guiding our gentle curiosity towards the next great mystery that awaits us. Our exploration of dark matter has taken us from simple jars to the frontiers of physics, and now to the ultimate quest. All of these impossibilities, these experimental challenges, these theoretical puzzles, ultimately reshape how we understand our universe. It sounds impossible, doesn't it? Well, in the vast cosmic theater, there's a profound mystery, a fundamental component of our universe that behaves in a similarly elusive manner. And that, my dear listener, brings us to the gentle impossibility of capturing what we call dark matter in something as ordinary as a jar. To understand why, we must first allow our minds to drift into the deepest reaches of space and contemplate what dark matter truly is, or more accurately, what we understand it not to be. Picture the visible universe, the twinkling stars, the radiant nebulae, the majestic galaxies. All this glorious cosmic scenery is made of what we call ordinary or baryonic matter. It's the stuff of you and me, of planets and sunshine, of every atom we can touch, see, or measure with our familiar tools. But this ordinary matter, as wondrous as it is, accounts for only about 5% of the universe's total mass and energy. A tiny fraction, isn't it? The remaining overwhelmingly large portion of the universe's mass budget is hidden. About 68% is dark energy, a mysterious force pushing the universe apart. And then there's roughly 27%, more than 5 times, all the ordinary matter combined, that we call dark matter. It's a silent, invisible presence, a cosmic scaffolding upon which the universe is built, yet it remains utterly unseen. We know it's there, not because we've seen it directly, but because of its profound gravitational embrace. Imagine watching a grand cosmic waltz, galaxies spinning, clusters of galaxies moving in concert. If all we saw were the visible stars and gas, these dances wouldn't make sense. The galaxies would simply fly apart, their individual stars flung into the void. But they don't. They hold together, held by an unseen extra-gravitational tug. It's as if an invisible hand is guiding their pirouettes, a hand woven from dark matter. This invisible hand leaves other fingerprints too. Light from distant galaxies, journeying across billions of light years, sometimes passes through colossal clumps of dark matter. And just as a glass lens bends light, these invisible masses bend the fabric of space-time, causing the light to distort and magnify, a phenomenon we call gravitational lensing. The cosmic microwave background, the faint echo of the Big Bang itself, also carries subtle patterns that whisper tales of dark matter's influence on the early universe. So, if it's so abundant, so influential, why can't we simply scoop some up? Here lies the core of its elusive nature. The dark in dark matter isn't just about it being invisible to our eyes. It means it doesn't interact with light, with electromagnetic radiation. This is crucial because all our everyday experiences of seeing and touching are fundamentally electromagnetic. When you see a friend's face, light waves are bouncing off them and entering your eyes. When you feel the warmth of a mug in your hands, electromagnetic forces are at play between the atoms in your skin and the atoms in the mug. But dark matter, we believe, simply doesn't participate in these kinds of interactions. It doesn't reflect light, it doesn't absorb light, it doesn't emit light. It sails through the universe like a ghost through a wall, utterly indifferent to the electromagnetic dance of ordinary matter. Think of it like a gentle breeze passing through a vast, intricate spider web. The web, made of ordinary matter, feels the wind, but the individual strands, if they were truly massless and frictionless, would not catch the breeze in a way that would allow you to collect it. Now let's bring our jar into the picture. A jar, whether made of glass or metal, holds things because its atoms exert electromagnetic forces on the atoms of whatever is inside. When you put a pebble in a jar, the atoms of the jar's bottom push up against the atoms of the pebble, preventing it from falling through. The electrons in the outer shells of the jar's atoms repel the electrons in the outer shells of the pebble's atoms. This is the essence of solidity, of containment. Dark matter doesn't experience these forces. If a dark matter particle were to pass through your jar, it wouldn't see the glass walls. It wouldn't collide with the atoms of the jar. It wouldn't be stopped by the electromagnetic repulsion of the glass molecules. It would simply pass right through, utterly unimpeded, as if the jar weren't there at all. It's like trying to catch moonlight in a sieve. The light flows through, unbothered by the mesh, because it doesn't interact with the solid structure in the way you'd need it to. Now, our leading theories suggest that dark matter is composed of new exotic particles, perhaps weakly interacting, massive particles, or WIMPs, or even ultralight particles called axions. The weakly interacting part of WIMPs is key. While they do interact gravitationally, their other interactions with ordinary matter are incredibly, almost impossibly, faint. They are so fleeting, so rare, that billions upon billions of these particles might be streaming through you right now, and you wouldn't feel a thing. They are like cosmic whispers, passing through you without a single rustle. This is why, instead of trying to capture dark matter in a jar, scientists build colossal ultra-sensitive detectors deep underground, shielded from all other cosmic noise. They are not trying to catch dark matter, but rather to detect an exceedingly rare, almost imperceptible nudge. They hope that just maybe 1 in a trillion dark matter particles might, by chance, weakly collide with an atom in their detector, causing a tiny, measurable recoil. It's like listening for a single, faint ping in an ocean of silence. So, while the quest to understand dark matter continues, we can rest assured that our jars, as useful as they are for fireflies or marbles, will remain empty of this cosmic mystery. It's a beautiful reminder that the universe holds secrets far beyond our everyday experience, secrets that challenge us to think in new and imaginative ways, stretching the very boundaries of our understanding. And as we drift deeper into the night, we can ponder the silent, unseen rivers of dark matter flowing through us, through our homes, and through our entire planet, always present, yet forever just beyond our grasp. Perhaps, in our next quiet moment, we can explore how these invisible rivers shape the grand cosmic tapestry around us. And so, as the day gently folds itself into the quiet embrace of night, we come to the soft, shimmering conclusion of our little journey together. We spoke of jars, didn't we? Simple, ordinary jars, the kind that might hold starlight if only we knew how to catch it, or perhaps the whisper of a summer breeze. And we wondered, with curious hearts, why such a humble container could never, ever hold something as vast and vital as dark matter. Think back now to the beautiful mystery we explored. Remember how we imagined dark matter, not as a swirling cloud we could see, nor a shimmering gas we could breathe, but as something far more elusive, far more subtle. It's not a thing that knocks or bumps or even gently brushes against the particles that make up your hand or the glass of a jar, or even the very atoms that form our earth. It simply passes, like a soft, silent thought passing through your mind, leaving no trace behind but the quiet hum of its presence. We discovered that dark matter isn't made of the familiar building blocks that make up everything we know and touch and feel. Not the tiny protons or neutrons, not the busy electrons. No, it's crafted from something entirely different, something truly alien to our everyday experience, yet utterly essential to the grand tapestry of the cosmos. This difference is key, isn't it? It's the very heart of why our jar, no matter how carefully placed, how securely sealed, would always remain empty of this cosmic ghost. Imagine for a moment the countless streams of dark matter flowing through you right now, as you lie warm and safe, drifting towards slumber, through your soft blanket, through your gentle breath, through the very bed beneath you, and indeed through the entire planet. It moves with an exquisite indifference, a silent dance that never pauses, never collides, never once acknowledges the presence of the solid world we inhabit. And a jar, for all its sturdy intention, is simply another part of that solid world. It offers no resistance, no barrier, no whisper of an embrace to something that chooses to interact with almost nothing at all. Isn't that a truly remarkable thought? To know that such an immense and pervasive part of our universe can flow through us, around us, and past us, utterly undetected by our senses, unseen by our most powerful telescopes, and uncaptured by our cleverest inventions. It is a profound testament to the sheer depth and breadth of the universe's wonders, a reminder that so much exists beyond the immediate reach of our understanding, beyond the simple grasp of our hands. This journey we took from the idea of a jar to the vast, invisible currents of the cosmos was not about finding an answer that neatly fits into a box. Instead, it was about expanding our sense of wonder, about embracing the quiet humility of not knowing everything, and finding beauty in the very impossibility of capture. It's a gentle lesson that some of the universe's greatest secrets are not meant to be held or contained, but rather to be appreciated in their boundless, free-flowing nature. And that, perhaps, is the most reassuring thought of all as you prepare to close your eyes. The universe, in all its complexity and mystery, is not a chaotic, frightening place. Instead, it's a place of elegant rules, of unseen forces, and of a quiet, persistent order. Dark matter, for all its elusiveness, plays its role perfectly, silently weaving its gravitational influence through galaxies, holding stars and worlds together in a dance as old as time itself. It is a gentle, steady hand, unseen but undeniably present. So now, let your thoughts drift, like those streams of dark matter, freely and without effort. Let go of any last questions, any lingering curiosities, and simply allow yourself to be cradled by the soft quietude of the night. The stars outside are beginning their slow, majestic journey across the sky, and the unseen universe continues its silent work, full of mysteries still waiting patiently to be understood. There is no need to capture anything, my dear one, as you journey into your dreams. The vastness of the universe, with all its secrets and all its wonders, will be there waiting for you peacefully and patiently when you awaken. For now, simply rest. Let the quiet darkness be your guide, and may your dreams be as vast and as full of wonder as the universe itself. Good night, little stargazer. Good night.